All right, so last time I think we were talking about hydrocarbons. So effectively we did not mention the concept of a functional group, but this will be an idea of a functional group. The first functional group that we're going to learn about is a hydroxide. Okay? When you take a hydrocarbon, say the simplest alkane such as methane, remove one hydrogen and replace it with hydroxyl group, you'll get an alcohol. Okay? So methanol is the simplest one of them. When you do the same, but you replace one of the hydrogens found in the benzene, you get phenol. If you replace a hydrogen with a group that is SH, pretty much like take a look at the periodic table quickly. You see where oxygen is? You see that the sulfur right under it? Oxygen and sulfur chemically have, fairly similar properties. So will thiols behave to some extent like alcohols? Yes, they would. Slightly different, they would. Okay? And then there's ether. I'm going to talk how to make an ether. In ether, oxygen connects to hydrocarbon residues. So what is the importance of this functional groups? OH group in alcohols and phenols, SH group in thiols, and oxygen in ethers. They convey new properties to the molecules that this ether or thiol or phenol or methanol were derived from. The properties of methanol, for example, are drastically different from the properties of methane. So what we do when we name them. So if you have methane and you derive, this is methane, and you derive an alcohol from it, you change the last letter E to OL, methanol. Okay? Same idea, ethane, ethanol. Now, common names are used, but more in non-chemical speech. Common names like methyl alcohol, ethyl alcohol, propyl alcohol, but for the most part, we should be comfortable with methanol, ethanol, propanol, and so on and so forth. So, a couple of links here. Well, I don't have to mention that ethanol has been known as an intoxicating drug for a long time. Most likely it was discovered by consuming fermented fruits. Okay. It mostly is produced by the fermentation of glucose. In some cases it can be a fermentation of fructose, right? So it's a classic alcoholic fermentation, the one that we use to produce things like beer or strong liquor or wine. Okay? So another way to produce ethanol is to facilitate the reaction between the ethene, the simplest alkene, the simplest hydrocarbon with one double bond, and water. Now, interestingly enough, this ethanol technically is cleaner than the one produced by fermentation, because fermentation is rarely a single process that occurs in whatever fermentation tank you are using. There are other byproducts that can actually make already poisonous substance, which alcohol is, even more poisonous. Okay? Most ethanol in the United States is derived from corn fermentation. This is actually what the main sort of goal of growing corn in the US is. I just wonder, asking you, this alcohol that is produced in the United States, most of it, what is it used for? Do you know? All this fermented corn that gives us a lot of alcohol, what this alcohol is used for? Hint, it's not drinking. Huh? No. No. It's not a lot. Like, we drink way more than we use rubbing alcohol, but it's still not drinking. Gas. They add it to gasoline. 10% ethanol, you know? So another interesting compound that belongs to alcohols is glycerol. Now, check out the names. It's going to be useful to learn nomenclature using that example. So how many OH groups do you see in glycerol? 3, right? So each group is alcohol, OL. But since there are 3 groups, it's triol. And then 3 carbons correspond to propane, so propan, okay? And the numbers reflect where this hydroxide residues are located. Okay? Now, when soaps are made, they're usually made from fats, okay, or oils. And during this process, also known as saponification, one of the products is glycerol. Glycerol is easily dissolved in water. It is very safe, and it is one of the best skin softeners that you can find, surprisingly. I can tell you, my dad, when he worked as an electrician, he had to work with a lot of aggressive chemicals and stuff, and he would have a bottle of glycerol. It was way before all these fancy lotions and creams were invented, and it worked marvelously well. Actually, when you use hand sanitizer, this gooey stuff, the gooiness of hand sanitizer is due to the addition of glycerol. Okay? And here's another, what's called polyatomic alcohol with 2 hydroxyl groups called ethylene glycol. And technically speaking, okay, it's ethanediol. You see what I'm saying? Okay. It should be 1, 2 to signify that it's 1 and 2. Okay? Di 2 hydroxide residues. So ethylene glycol, probably the most the moment or the process in which you actually interact with ethylene glycol is when you fill up the radiator in your car. Okay? The radiator fluid contains ethylene glycol. Okay? So it is an antifreeze. Solvent, yes, but here's an important thing. Yes, its sweet taste is indeed attractive to pets and children, so there are cases of kids finding ethylene glycol, drinking it. This is why often it is. So the reason why antifreeze for your car has a color is mostly to sort of repel kids. Like, they're not going to drink bluish stuff. You see what I'm saying? Or, okay, less likely. Yes, less likely to drink bluish stuff. Okay? Now, why is it bad? Because as pretty much any other alcohol, it will be oxidized by the enzymes in the liver, forming so-called oxalic acid. And oxalic acid will form salts in the kidneys, which will result in a kidney damage. Okay, so far so good. Now, this one is bisphenol A, an infamous, you see, bis, 2, meaning 2, phenol. So 2 phenol residues sitting on the central atom of a propane. So it was used as an additive during the manufacturing of beverage bottles. Okay? Does that make sense? Anyone has a plastic beverage bottle? Well, you do. It's not plastic, it's glass? Well, I do. Okay. That'll work. I mean, I know that I do. So when I look at the bottom of my bottle, it should say BPA free. Probably does. It's just very, very small and I can't really see clearly. So BPA free, turns out when these bottles are washed, small amounts of BPA can leach into the water, very small amounts. And the biggest problem is that BPA disrupts certain endocrine processes. So it has a long-term toxicity. And turns out bottles without BPA are just as good as bottles with BPA. It was a matter of convenience. So you see, we mentioned that structure before, the benzene ring, right? The aromatic ring. So first of all, the reason why it's called aromatic, because they smell. Not necessarily good. Okay? They just smell. But aromatic compounds can be found in many naturally occurring aromas, such as vanilla or thyme. Does that make sense? So all these spices, effectively chemicals. Any questions on the alcohols, like structurally? Okay. Thiols, pretty much like an alcohol, but they contain sulfur. One of my favorite compounds to talk about, not as much to work with. So this is thiol group in this butene thiol. Okay? You can see that one of the statements that is made here is that thiols often have, they gently called it disagreeable odors. All right? When you start crying when you cut the onions, this is because of sulfur organic compounds, mostly thiols, found in onions. When you sense the smell of garlic, which some people don't like, this is thiols. Okay? That makes sense? Now, to give an idea, does anyone have a gas stove? No? Okay. If you open, like, let's say you are grilling on the gas and you open the tank, can you smell the gas? Turns out you can't, right? Turns out the actual propane has no odor. One of the sulfur organic compound that is called ethyl mercaptane, which is added in extremely small amounts to detect the leaks. It is considered to be one of the smelliest compounds, if not the smelliest compound known to humans in terms of the number of its concentration in the air, so you can sense the smell. And I'm going to give you a little bit like to sort of brighten up the conversation. So this is pretty much a description of people who work with sulfur organics. I graduated with a degree in chemistry, and all my chemistry classes were in the same building. And when my friends tried to stop by and meet me in a hallway, they always complained that the entire building smells like, well, chemistry, very unpleasant. I did not feel it because I got used to it. but we had a lab where people worked with sulfur organic. That was a bit much even for me. The story goes that they had to have a separate set of clothes for the lab, and they still stunk. They stunk so much that when they walked into a subway car, homeless guys left. The only way to get the smell out of the hair was to shave completely. They not super toxic, but they absolutely stink. Just horribly stink. Okay? So when you name thiols, you take the name of the hydrocarbon and add thiol to it. Super simple. Okay? Ethane thiol, 2-butane thiol. Why 2? The number 2 shows the position of the SH group in the thiol molecule. Sounds good? Everybody, questions? Okay, let's talk about ethers. So ethers contain an oxygen that connects to carbons. Okay? These carbons must be either hydrocarbons like alkylic, methyl, or, for instance, it can be this. They can be aromatic. Okay, good. So the simplest ether is dimethyl ether. How do we derive the name? This is a methyl group. Agreed? This is a methyl group. So 2 methyls make dimethyl ether. Okay? Now, for instance, here, one group on the left of oxygen, it's methyl. On the right, it's propyl. So, methyl, propyl, ether. Okay? We're going to be using the common names. So, ethers, actually dimethyl ether, if my memory serves me well, was the first chemical used as an anesthetic. Just when do you think anesthesia was, period-wise, like year-wise, was actual anesthesia, like knocking the patient out, when doctors started to use it?
Early 20th century.
Not that bad. Not that bad. Better, mid-19th century, okay? Just FYI, since we're talking about phenols, when do you think doctors started using antiseptic procedures in surgery? Go on. Mid-19th century. So imagine that, and not, for instance, antiseptic procedures and anesthesia were not used during the Civil War in the United States. Not yet. They didn't reach the United States yet. What was used as anesthesia? Whiskey, internally. There was no antisepsis, so more people died of wound infections that were killed on the battlefield. Mm-hmm. Yep. So, dimethyl ether was the first anesthetic. Here's the problem. Ethers are extremely combustible. You understand the term, the ignition temperature? Like the temperature at which they're going to start burning? For dimethyl ether, the ignition temperature is 54 degrees Celsius, if I remember well. I mean, it's lower than the boiling point for water. It's extremely flammable. So you can either use like a cloth with ether to knock the patient down, but it's going to work only for so long. Or you need to provide some kind of vapors so the patient breathes them over time. Here's an issue. You basically saturating the room with highly flammable gas, vapors, that can explode at any moment. So eventually what scientists came up with is to replace hydrogens with fluorine and chlorine. Okay? So that reduced the volatility, less likely to get in the room, and reduced the flammability. Okay, they really not flammable. Does that make sense? To my knowledge, ethers aren't commonly used in human procedures, but in animal procedures, isoflurane is one of the most common short-term and quick anesthetics. I used to work with mice, and when I needed to knock mouse out for surgery, I used injectable anesthetics. But when I needed to run a quick procedure, like I had to do the nasal drops in mice, you put them in a box with a little bit of isoflurane, it knocks them out in 5 seconds. You grab a mouse, do the procedure, like put it in a cage, and it's back on track in like another 15-20 seconds. It runs out pretty quickly. Okay? So let's talk about chemical properties of alcohol. So first of all, the classification, which actually will determine some properties. Alcohols can be primary, secondary, or tertiary. So let's figure out what it means. So this carbon, to which hydroxyl group is attached, this carbon has a connection, a bond, to only one other carbon. Does that make sense? Okay? So if this carbon is what's called monosubstituted, it is a primary alcohol. In case of isopropanol that you see here, hydroxyl group is attached to a carbon, which in turn forms bonds with two more carbons. 2 means secondary alcohol. And finally, this 2-methyl-2-propanol, or isobutanol, okay, is a tertiary alcohol. Good? So the carbon which holds hydroxyl group is connected to 3 other carbons. So in order to learn this, let's go through this classification. A, is it primary, secondary, or tertiary? Secondary, because 1 and 2, the connections, right? B, primary, secondary, or tertiary? Primary. And C obviously is tertiary. Sounds good? Now, remember electronegativity, kind of in general, the whole concept. Do you remember which corner of periodic table harbors the most electronegative elements? The right top, right? Right top corner. Oxygen is the second most electronegative element in the periodic table, right? Which means it's going to pull the electron density to itself. So, in the molecule of alcohol, electron density is shifted towards oxygen, both from carbon, okay, and from hydrogen. Which makes this oxygen atom being slightly negatively charged and this hydrogen atom being slightly positively charged. Good, everybody? So, which means this group is it's polar group. Which means this polar group will readily form hydrogen bonds with water molecules. But here's the catch. In addition to polar OH group, alcohols also have nonpolar hydrocarbon tails. Making sense? Hydrocarbon tails that consist of carbon and hydrogen only are, well, nonpolar. And the story about solubility of alcohols is pretty much which character, polar or nonpolar, dominates in the molecule. Okay? So essentially alcohols that have 1, 2, 3 carbons, namely methanol, ethanol, and propanol, are soluble in water. As you start increasing the number of carbons, the solubility goes down. So for instance, butanol, which has 4 carbons, is soluble, but to some extent. But when you get to pentanol, it does not mix with water. Are we good so far? Questions? Okay. So we use alcohols for, well, in sort of life, daily life applications. We use alcohols for 3 main reasons, if you think about it. We use them as an intoxicating drug. We use them, in some cases, as a solvent. And we use them as a sanitizing chemical. For instance, I would include here hand sanitizers. I would include here mouthwash, which contains alcohol as well, right? So I told you before that when chemists start writing about the topics they have very little idea about, they manage to get a bunch of statements wrong. So we're going to go through these statements and we can just give them shit, okay, altogether. So first of all, used as an alternative to washing hands. No, they shouldn't. These 2 procedures are complementing each other rather than replacing. Why? Because while they do kill most bacteria and a certain number of viruses, for instance ones that cause coronavirus or influenza, alcohols do not have any effect on the viruses that cause common cold, the rhinovirus. Or, have you heard about norovirus? The 2-bucket disease, the winter vomiting bug, which was discovered in the city of Norwalk, Ohio. They have no effect on it. The only thing that you can do is wash your hands. Okay? They got right with the concentration, 60 to 85%. They are only highly flammable if you set them on fire. So what I'm trying to say is, if you work with compounds like dimethyl ether, even an electric spark can cause an explosion. If I have a bottle of hand sanitizer on my desk, I can have a candle next to it and I'm going to be fine. Okay? Now, may they contain triclosan? The answer is not anymore. Triclosan was a very, very interesting drug, which was found to be, it's one of the phenols. You see the OH group on the aromatic ring. So, triclosan was used mostly in the soap as an antibacterial additive, but turned out it wasn't too effective, and also the accumulation of triclosan in the groundwater, detectable accumulation, resulted in triclosan-resistant bacteria. Okay? Not antibiotic resistance. This is wrong. This is plainly wrong. Triclosan is not antibiotic. Okay? Good? Now, solubility of phenols. They are slightly soluble in water. That is true. As a matter of fact, phenol, this compound, has the melting temperature at about 35, 36 degrees Celsius. So when I was in college, I wanted to prove this, so I got a piece of phenol and held it between my fingers for 15 minutes. I proved 2 things. First, it's going to melt between your fingers. Thing number two, I'm an idiot because it's a very strong irritant and I had a chemical burn on my fingers for some time. So they do produce this phenoxide ion, so effectively phenol works as an acid. Does that make sense? The hydrogen dissociates and binds to water, forming hydronium ion. They were used as antiseptics. So the first proper surgical antiseptic use was invented by Joseph Lister in England in 1960 something. But so let me put it in the perspective. The solution of phenol in water back then was called carbolic acid. Surgeons would wash their hands with carbolic acid, pretty much rubbing for the surgery. And it is such a strong irritant that they had chronic eczema just from washing their hands. Lister used carbolic acid as an antiseptic in the surgery on the patient. Carbolic acid would be sprayed into the surgical wounds to prevent an infection. Can't even fathom what the patient was feeling. Questions about alcohols and phenol so far? All right. Aldehydes and ketones. We don't interact with aldehydes as much in our day-to-day life, but we do interact with ketones, namely acetone. So aldehydes and ketones share the same functional group, which is a carbonyl group. In carbonyl group, carbon forms two bonds with other carbons and forms a double bond between carbon and oxygen. Now, remember our conversation about electronegativity. Right? I mean, the fact that oxygen will pull electron density towards itself. Turns out, the more bonds you have, the more electron density will be shifted towards oxygen. So effectively, in carbonyl group, oxygen accumulates some negative charge, and in addition, has two lone pairs, so a lot of electron density. Carbon, on the other hand, has a positive charge. Now, if you look at this bond, this arrangement, it forms a dipole, essentially. Let me erase all of this. So this is a dipole, with that pole being negative and with that pole being positive. Okay? And that will actually determine the solubility and the properties of ketones and aldehydes. Now, what distinguishes them? So you see the carbonyl group, right? Well, if you place the carbonyl group at the end of the carbon chain, you can get an aldehyde. Okay? If you put it, now, hear me out, not necessarily in the middle, but not at the end, you can get a ketone. Okay? So, you have two simplest examples. Well, okay, you have a simplest example of a ketone. It's acetone or propanone. And the second simplest example of an aldehyde, which is called ethanol, or we're going to talk about the naming in a minute. Okay? All good? Okay. So when we write a formula for an aldehyde or a ketone, as you may have learned, we sometimes can replace the carbonyl group, the group that is characteristic for aldehydes, as just CHO collapsing all the bonds, and carbonyl group of a ketone can be written just as CO. All right, make sense? Cool. Now, there are IUPAC names, and they're common names. So let's talk about aldehydes. What's the name for that compound with one carbon? The proper name. Anyone remembers? Can't hear you. No. Just this one. Hold on a second. No. What I'm saying is this. CH4. A hydrocarbon. What is the name of it? The simplest hydrocarbon. The M word. Methane. Methane. The simplest aldehyde is going to be this. Okay? Good? Same number of carbons. So we took methane and replace E with Al. Okay, does that make sense? Now let me roll up a little bit. You see this fella? How many carbons? 2. What's the name for the hydrocarbon with 2 carbons? The E word. Ethane. So what I did, I replaced E with Al to get ethanol. Good? So for first 4, thank you. For first 4, there are also common names. Just kind of memorizing. Formaldehyde, acetaldehyde. So, sorry. In terms of, methanol, ethanol, propanol, butanol. 5 and further, we just use the proper IUPAC names. So this is basically the illustration of what we just talked about. Methanol, ethanol, propanol, butanol. Do we need to add numbers to indicate where carbonyl group is? You think so? In aldehydes, where is a carbonyl group? It's always at the end. So you don't need numbers. You see what I'm saying? The position is fixed. Like if it's an aldehyde, it's at the end. Now the ketones, you replace E at the end of the hydrocarbon with ONA. So this is the simplest one, right? Acetone, which is called propanone because this propan thing signifies 3 carbons, and then we add ONE. Now, do we need to add any number to show where carbonyl group is for propanone? We don't, right? Because the only position it can be is this, right? Because if you put it at the end, it's not a ketone anymore. Now, what about butanone? Do we need a number? Think so? Okay, hear me out. These 2 molecules, the one that I just drew and the one under it, are they equivalent? They are. Because there's no difference which carbon will be number 2. You see what I'm saying? Does that make sense? Yes, or just... Yes, because if we flip it, like if we do this rotation around the vertical axis, we're going to get this molecule. So they're not different. When we start talking about 5 carbons, we need numbers. So this would be 3-pentanone. If I would put carbonyl group here, it would be 2-pentanone. Making sense? Okay. Now, what about this fella? This gets a little more complicated. But here's the thing. How many carbons are in the ring? 6. Right? Hexane. They are organized in the ring, so cyclo. The more important functional group, there's a ranking of functional groups, but the more important functional group is carbonyl. So this is why it's cyclohexanone. What is the rule about numbers in general? What should you strive to achieve when you're numbering something in organic compounds? The smallest total number, like if you add them all together. So we don't give a number 1 because all carbons are equivalent. Does that make sense? So whatever it is, but we're going to assign number 1 here, 2, 3. So at the 3rd position, there is a methyl group. Does that make sense? We don't say 3-methyl 1-cyclohexanone because why? Since we know methyl, we know the number for oxygen. So similarly to alcohols, ketones and aldehydes can be dissolved in water. Now, same idea. This carbon-oxygen double bond, remember, it's very polar. So there's a fair amount of positive charge in carbon and a fair amount of negative charge in oxygen. And they form hydrogen bonds with water. Again, when 4 or less carbons, so basically, let's say formaldehyde, acetaldehyde, propylaldehyde, and butyraldehyde, the first 4, are soluble in water. Okay? Does that make sense? So whether it's an aldehyde or a ketone, if they have 4 or less carbons, they're polar enough to be soluble. If they have 5 and 6, solubility drops very quickly. So we use actually quite a few of ketones as solvents. Acetone, nail polish remover. Okay. Now what about aldehydes? It's probably the most famous is formaldehyde. When you make a solution of formaldehyde in water called formalin, okay, it kills all the bacteria. You can throw a sample in the formalin and it will be preserved for hundreds of years even. Okay? Does that make sense? Another application of formaldehyde, which I learned myself, disinfection of buildings. I used to work in the lab with dangerous pathogens, pretty much, okay, biosafety level 3, and once a year it had to be decontaminated. And it was decontaminated by pumping formaldehyde into HVAC system, turning it off and letting it sit for 2 weeks, and then it will turn it on. It will remove all the formaldehyde from the circulation, and then you walk in and start cleaning crap, and in 2 hours you get out because your head is killing you, since not it really smells bad and it's toxic. So you get slight formaldehyde poisoning. A lot of aldehydes are smelly. You encountered cinnamaldehyde in the lab on Monday. It gives the odor to cinnamon. Vanillin, vanilla, and benzaldehyde smells like almonds. Okay? So let's go over aldehyde or ketone. A, aldehyde or ketone. B, C, and D. Yes. So, the reactions. Well, first of all, when you have OH group on one carbon and hydrogen on another, you can try and remove them both to combine water, all right, creating a double bond. So this is called a dehydration reaction. Am I making sense? So we'll take ethanol, the simplest, well, not the simplest, but fairly simple alcohol, and provide acidic catalyst and heat. You can get an alkene here, the ethene, an ethylene. Okay? Probably more interesting is the reactions of oxidation and reduction as they relate to alcohols and ketones. I'm going to give you so what I'm going to say now is basically a crash course, not for the exam, but for the general understanding. Okay, so hear me out. If you have a molecule A, and this molecule A gives an electron to a molecule B, okay, this is the oxidation reduction process. The molecule that loses an electron is oxidized. A is oxidized by B, and B is reduced by A. Okay? What? No. No, I can guarantee you that. So A, since it loses, so acceptance of electron is reduction. B is reduced. But B oxidizes A, if that's what you meant. And A reduces B. Reduction is gaining an electron. Oxidation is giving away the electron. We can chat. It's an English language problem. It's not a chemistry problem. Okay? But in organic chemistry, it's often hard to track the electron movements. So what instead we track the formation and breakdown of the bonds between carbon and oxygen. Okay? So, when something is oxidized, it means that carbon and oxygen form more bonds as the result of this reaction. Products contain more bonds between the carbon and oxygen than the reactants. And reduction means, well, decreasing the number of bonds between carbon and oxygen. Make sense? So let's take a look at the oxidation of alcohols, right? So this is a primary alcohol. Everybody agrees? It's ethanol. Good? When it is oxidized, How many bonds between carbon and oxygen do we have in the reactant? 1. And in the product, 2. So we have more carbon-oxygen bonds. This is why the primary alcohol has been oxidized to acetaldehyde. Okay? Good? That's not the end, because aldehydes can be further oxidized to produce an acid, a carboxylic acid, which we didn't yet cover. How many carbon-oxygen bonds do we have on the left? And on the right? 3. So, acetaldehyde, acetic acid. Sounds good? Before we move on, I'm going to tell you the importance of this. Well, we're going to discuss how it is relevant medically. This is ethanol. When people consume ethanol, well, it's a poison. So ethanol is converted by the enzymes in the liver first to acetaldehyde. But acetaldehyde is also poison. So there's a second enzyme that converts acetaldehyde into acetic acid. Cells can use acetic acid. It's an energy source, technically speaking. Okay? But here's the problem. Well, it kind of explains, not a problem, it kind of explains one of the mechanisms of the hangover. When people overconsume ethanol, they overeat, they go over the liver capacity to neutralize it. So liver would oxidize it to acetaldehyde, but will fail to completely oxidize it to the acetic acid. Accumulation, this is really toxic. Accumulation of acetaldehyde is bad. One of the reasons why, people in the morning after heavily drinking feel crappy is acetaldehyde. Okay? Does that make sense? Now, that's not the end of the story. Now, this is a secondary alcohol. Agreed? This is the 2-propanol. Good? So when it's oxidized, instead of forming an aldehyde, it forms a ketone, in this case, acetone. Okay? Can acetone be further oxidized? Can this carbon form any more? No. This carbon has full bond capacity. It can't form any more bonds with oxygen without breaking the actual chain of carbons. Okay? Now, I want to practice something with you for a second. We have methanol here, and the first oxidation of methanol will result in what? Class of chemicals. Methanol is an alcohol. We oxidize it, and we get what? We get aldehyde, right? And then we oxidize that aldehyde, producing what? The answer is literally on the screen. An acid. Okay? So, this is methanol, and this is formaldehyde. and this is formic acid. What did I tell you about formaldehyde? This image on the right. What did I tell you? What do we use formaldehyde for? Preserving. You know, disinfecting the rooms. Is it toxic then for humans? If we can preserve tissues like everything, all cells die. Toxic. Okay. So, if a person consumes methanol, for an average male like my size, the lethal dose is about 4 to 5 ounces, fluid ounces. Okay? It is used, obviously legally, at least, well, in some countries, poorer countries, to produce counterfeit alcohol, like counterfeit vodka. It causes very severe poisoning. The first symptom is blindness, and it's irreversible blindness. So people will, you can treat it. Now, does that make sense? Now, the treatment, if somebody consumes large amounts of methanol and is promptly diagnosed, the treatment is, it is true, it's not like an urban legend. First thing that physicians will do with a person with methanol poisoning is flush that person full of ethanol. Ethanol replaces methanol in cells. Does that make sense? Basically kicks it out. And now physicians have to treat garden variety alcohol poisoning, ethanol poisoning. Basically the person becomes incredibly drunk. Well, for a reason. Ethylene glycol, the antifreeze poisoning, same treatment. Absolutely. Flooding the patient with ethanol and then dealing with this, because it can push it out as well. Does that make sense? Now, only ethanol and propanol are used in products like hand sanitizers. Why? Why not methanol? It's very cheap to make. I gave you the reason just 1 minute ago. Go on. Yeah, because people will drink anything that says alcohol on it. Okay? Now, let's say somebody decides, my cultural background implies that anything that contains alcohol should be consumed. I know quite a few people who drank unimaginable things and survived. But let's say somebody drinks hand sanitizer, which contains ethanol. It's not going to taste good. Are they going to get drunk? Absolutely. The liver is not going to thank them because there are other compounds that have to be detoxified, but it's okay. Now, what if they drink hand sanitizer that contains isopropyl alcohol or 2-propanol? It will be oxidized into the acetone, and that's it. So people will develop ketosis. So technically speaking, if somebody consumes propanol or acetone, is it poisonous? Yes, but it is much less poisonous than formaldehyde. Okay, it's kind of in the middle. Tertiary alcohols cannot be oxidized without breaking the carbon bond. Okay? Does that make sense? Well, this is what we just talked about. Methanol poisoning. Okay? Does that make sense to you? Just a sort of a fact. Formic acid. Familiar with fire ants?
Fire ants?
Yes. The burning sensation is because of formic acid that they inject in the wound. And when, at the dawn of organic chemistry, when scientists didn't know how to get from methanol to formic acid, the easiest way to produce formic acid was, guess. Ants were placed in a flask, heated up, and formic acid simply evaporated from the bodies. And then could be collected. Okay? Ethanol, yes, it is a depressant. It depresses the part of the, yeah, okay. I'm talking about biological, neurological way. We have depressants, and we have substances that excite us. Alcohol depresses the activity of the part of the central nervous system called reticular formation. This is why, for example, it shouldn't be taken with other depressants such as benzodiazepines like Valium or barbiturates. Okay? The combination can kill a person. Right? This is true. Kills or disables more people than any other drug. Absolutely. Yes, consumption can be analyzed using breathalyzer. So the metabolism, the comparison of alcohol metabolism between social drinker and alcoholic is staggering, right? Now, to be fully clear, first of all, it depends on the genetics. One of the factors why, so which people of which racial background are most prone to developing alcoholism? No. It's not a racial background, it's cultural. No, I'm talking racial background. Asians, I mean like Japanese, Chinese, Native Americans because they descend from them, and Pacific Islanders. Those groups genetically have low level of the enzyme called alcohol dehydrogenase. So they do not metabolize alcohol really well. They get inebriated much faster genetically, and they develop alcoholism much faster as well. Okay? Does that make sense? Second thing, you probably know, like, it's not a secret, everybody's here is over 21, I suppose. People have different tolerance to alcohol. Two things. First, genetic. Some people are genetically more tolerant. Second, a habit. Okay? People who are alcoholics, they have basically well-trained liver. Okay? It's some kind of a liver CrossFit, if you think about that. Okay. Now, what about thiols? So thiols can be oxidized, but in a slightly different way. So you need two thiol groups being near each other, okay? And then you remove these two hydrogens and slap them on oxygen. So you produce disulfide bond. These bonds are extremely important in maintaining the protein structure. Okay? Does that make sense? Now, here's an example of how the knowledge of such basic organic chemistry can be applied to the day-to-day life. We all have differently shaped hair. Can be straight, can be curly. The shape of the hair depends on the structure of the protein called keratin. In our hair, it's different between the people. And one of the major determinants of the structure are disulfide bonds. When people want to straighten up their hair or, conversely, make them curly, what do? So again, heat and sometimes chemicals. Heat and chemicals destroys these disulfide bonds. What happens to straightened hair over time? When people straighten their hair, do they straighten them forever? No, they get back. These bonds are reformed and the shape of keratin is restored. Okay? Okay. I know that it's for the record. It goes, but sorry, lightweights. Like, if you would tell any average Russian male that this is like 4 beers is loss of inhibition, again, genetics, age, habits, mass, body mass, even when people drink and eat, even food consumption effects, the pace effect, it all is absolutely biochemically explainable. For example, the fastest absorbing concentration of alcohol is about 20%. This is why many cocktails get people inebriated much faster than strong alcohol, which takes way longer to absorb. Okay? Consumption of fat results in the protective layer and reduces the absorption of alcohol in the stomach. I'm not saying that alcohol will kind of be removed. It will absorb. Eventually, it will catch up with you, but the pace at which people become inebriated when they consume food will be different from, just drinking. Make sense? I will, during the break, I don't want to put it on YouTube. I will comment on this. Okay? Yeah. I will comment on this. Now, an interesting test that allows you to determine whether there are aldehydes is the tolerance test. So in tolerance test, you have ethanol, an aldehyde, and silver ions, ketones. Okay? So silver acts as the oxidizer, removing electrons from ethanol, and that forms acetic or ethanoic acid. But look what happens to the silver. It is converted from ions into the metal. And this metal, I did that test like ages ago. This metal will cover, if you do it in the tube, it will cover the inside of the tube. Okay? In Russian, when I studied chemistry, it was called a reaction of a silver mirror. Okay? Now, another important test, Benedict's test. We're going to talk about Benedict's test when we get to carbohydrates. So, Benedict's reagent contains bivalent copper. Okay? And it will determine very specifically, check this out, only if there is a hydroxyl group next to an aldehyde group. Does that make sense? It's not going to work if there is no hydroxyl group here. Do you follow my train of thought? So when you mix an aldehyde, such as 2-hydroxypropanol, which contains hydroxyl group adjacent to an aldehyde ending, it will reduce copper and oxidize hydroxypropanol to hydroxypropanoic acid. Now, Benedict's reagent is blue. When the reaction happens, the color of the solution changes to bright, dark red, literally brick red. You can see it here. Okay? So this is what we use Benedict's reagent for. This is the glucose. Okay? This group, aldehyde or ketone. Aldehyde at the end, right? Does it have adjacent hydroxyl group? It does. Benedict's test will result in the oxidation of glucose to gluconic acid and reduction of copper in Benedict's reagent to copper monoxide, which is brick red. Okay? There are other ways to reduce aldehydes and ketones. Basically, I'm going to get it here. Check this out. So you have an aldehyde, right? using hydrogen or sodium boron hydride, doesn't matter. Using a reductant here and a platinum or palladium catalyst, you reduce that carbonyl group to hydroxyl group. Does that make sense? So you get primary alcohol. If you do the same with acetone, you get secondary alcohol. So basically, what I'm telling you is that we had a reaction in which, isopropanol was oxidized to acetone, right? Make sense? And this reaction that I just wrote is opposite to the reaction that you see on top. And the same, you can say the same about this. So what would be the product of oxidation of 2-butanol? What should I do? What should I replace OH group with? Double bond to oxygen, right? Okay. So, B. So when 1-propanol is oxidized, what's going to be the product here? When you oxidize the OH group at the end, that's going to be this, right? So number 3. And when you oxidize that number 3 even further, what's going to happen? Yes, exactly. Okay, good.